A-level physics, and this is for the electronics option, and this video is about capacitors and inductors in AC circuits. So capacitors, we know all about capacitors, and in a DC circuit we know what's going to happen when we close the switch. The capacitors are going to charge up and the current will fall exponentially, etc., etc. What about in an AC circuit? If we put a capacitor in an AC circuit, what's going to happen when we close the switch? Well, what will happen is that the capacitor will charge up with one of the plates positive and the other negative, and then it will discharge, and then it will charge up again the other way around as the polarity of the supply changes. As the supply goes from positive negative to negative positive, so the capacitor will charge up one way and then the other way, and you'll get charge sloshing onto one plate and off the other, and then doing the opposite, and the charge sloshing on and off the plates. Okay. Now, the voltage across the capacitor, there'll be a phase difference of 90 degrees between the voltage of the supply and the voltage across the capacitor. We say that the voltage across the capacitor lags. It's 90 degrees behind the power supply voltage. Now, why? Because it takes time for the capacitor to charge up. It doesn't respond immediately. You know, remember the time constant of the circuit and all that business. It takes a little bit of time for the capacitor to charge up, so it takes a bit of time for the voltage across the capacitor to get bigger. So we say the voltage across the capacitor will lag by 90 degrees. Now, capacitors in AC circuits act a bit like resistors. You know, if the capacitor wasn't there, then the current would be bigger. So they act like resistors. However, their, in inverted commas, resistance depends on the frequency of the supply. Okay? If the frequency is high, then the capacitor doesn't have very much time to charge and discharge. So it's not going to get very much of the voltage. If the frequency is low, then it has plenty of time to charge and discharge, so it will get a bigger share of the voltage. Now, this quantity here, strictly speaking, we don't need to know it. It's called the reactance of the capacitor. It's measured in ohms, so you don't need to know reactance, but it's the resistance of the capacitor in an AC circuit. The point about it, the important thing, is that it's inversely proportional to the capacitance. So basically, the smaller the capacitance, the bigger the resistance. The bigger the capacitance, the smaller the resistance. If we did a graph of the reactance, which is measured in ohms, so I'm just going to write ohms against frequency, yes, then it's inversely proportional. Okay. Now, this component is called an inductor, and it's basically just a coil of wire. Yes, and usually it's got like an iron core in it. Okay, depending on what value you want. Inductance has the symbol capital L, and it's measured in henries. What do we mean by inductance? What is inductance? Well, if you look at this circuit now, this is a DC circuit, obviously. When we close the switch, now what's going to happen is we're going to get a magnetic field in the coil. This is all to do with electromagnetism. Now, you remember Faraday's law, don't you? And Faraday's law basically says that when the flux changes, we're going to get an EMF, and the EMF is proportional to the rate of change of flux. Lenz's law says that the EMF will oppose the change in flux. So the power supply is kind of pushing current around the circuit, and it's making the flux bigger. So the EMF will work against it. The EMF will say, no, 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 no. And it will push back. We call it a back EMF. So you've got the EMF of the power supply trying to make the flux bigger, and then you've got this induced EMF opposing that from Lenz's law. So Faraday's law, Lenz's law, you need to know them anyway for the core. Okay, the power supply pushes the current that way, the back EMF opposes that because of Lenz's law. Now, in an AC circuit, what's happening is that the power supply voltage is changing all of the time. And because of that, the back EMF will be changing all the time, but it will always be opposing it. It'll always be working against the power supply voltage. And because of that, in AC circuits, inductors act like resistors as well. You know, the current would be bigger if they weren't there. And their resistance depends on the frequency as well. And this is now XL, that's the reactance of my inductor. And again, don't worry too much about it, but it's measured in ohms. So again, it's just like resistance. Yeah, it's the resistance of an inductor in an AC circuit. And it's measured in ohms. And look, equals 2 pi FL. So my reactance, and again, I'm just going to call it omega because it's like resistance. Yes, my reactance gets bigger with frequency, because when the frequency is bigger, then the flux is changing more rapidly. So from d psi dt, you're going to get a bigger back EMF. Again, there's a phase difference, but this time the voltage across the inductor, we say it leads Vs by 90 degrees. Don't worry too much about that, okay? But again, there's a phase difference. What's going to happen if we have an inductor and a capacitor in parallel in this circuit here? Now, the resistance, and I'm just going to call it resistance of the inductor, is bigger at higher frequencies. The resistance of the capacitor is lower at lower frequencies. So remember, for the inductor, it gets bigger with frequency. For the capacitor, it gets smaller with frequency. If we have both of them in parallel like this, then what happens is we find that there is a minimum at a certain frequency. And that's the minimum resistance. Now, when you've actually got both of them combined, it's actually called impedance, Z. It's measured in ohms. It's the resistance of a combination in an AC circuit. But the point is that it's a minimum at a certain frequency. And that means if you were to look at the current against frequency, then the current sloshing around in there will be a maximum. That's how the current will vary with frequency. Okay? And we say that it's the resonant frequency. Yes, the frequency where the impedance of the circuit is a minimum is the resonant frequency. Yes, what's actually happening in the circuit is very interesting. What's happening in the circuit, and we think about it in terms of energy. The capacitor stores energy, electrical potential energy, and then when it discharges, it gives that energy to the inductor, and the inductor stores energy as a type of magnetic energy. And then the inductor gets rid of that energy and it gives it to the capacitor, and the capacitor charges up. And so this energy is sloshing backwards and forwards and backwards and forwards. If you look at the diagrams below, and you can see what's happening to the capacitor when it's charged up, the current is zero, the back EMF is zero. When the capacitor is discharged, the current is a maximum, the back EMF is a maximum, and then it happens the other way round. So basically, the current is sloshing and the energy is sloshing from the capacitor to the inductor, from the inductor to the capacitor, from the capacitor to the inductor. Okay? Energy is continually transferred from one type to another. So the energy in the capacitor will vary, and the energy in the inductor will also vary, but they'll be out of phase with each other by 180 degrees. You remember that the energy stored in a capacitor is a half CV squared. The energy stored in an inductor is a half Li squared. So L is the inductance, remember, measured in henries. I is the current. So that's biggest when the current is biggest. The energy stored in the capacitor is like static. So it's biggest when the current is zero. The energy stored in the inductor is dynamic. It's bigger when the current is a maximum. There is an analogy. Look at this fantastic animation that I did on Flash here. We can draw an analogy between what's going on here and a mass on a spring. If you look at the mass on a spring, we've got elastic potential energy, which is a very static type of energy. Yeah, it's maximum when it's not moving. And then we've got kinetic energy, which is a kind of a very dynamic energy. It's maximum when the velocity is biggest. The elastic potential energy is a half kx squared. The kinetic energy is a half mv squared. So this situation is analogous to my LC circuit. Yes, static energy, kinetic energy, static energy, kinetic energy, static energy. So the two situations are analogous. The spring is analogous to the capacitor. The mass is analogous to the inductor. Now, my mass on a spring would keep oscillating forever if there was no friction. Yes, but there is friction. There's always friction, and so this system is going to lose energy every cycle due to friction, and we call that damping. Okay, now again in my LC circuit, we're going to lose energy due to any resistance, and there is always resistance. I mean, the inductor is a coil of wire. It will have a little bit of resistance as well. So we're going to lose energy due to the resistance in the circuit. We'll lose energy as heat every cycle due to resistance in the circuit. So that's a bit of electromagnetic damping, if you like. Okay. Uses of LC circuits. Uses of these circuits which resonate at a particular frequency. Well, one thing is if I want to produce a signal of a certain frequency, yeah, if I have an LC circuit which has a resonant frequency of 440 hertz, then that will produce a signal, a voltage of 440 hertz for me. Yes, so something like a synthesizer or whatever. Tuning circuits in a radio. Lots and lots of radio waves in the air. If I put my radio tuning circuit to a particular frequency, then it will resonate at the carrier frequency of radio 4 or whatever, if I want to listen to radio 4. So tuning circuits finds a single frequency from a mixture of lots of different frequencies. And then filters, band pass filters. There are high pass filters, there are low pass filters, there are band pass filters which let through certain frequencies or they stop certain frequencies. And music producers, when you're mixing your latest single and you'd want to make the bass sound a little bit louder or that frequency sound a little bit lower, then they do a lot of messing about with these filters to filter out or to boost different frequencies. So band pass filters they're called. Here's a band pass filter. So this circuit is used to select a narrow range of frequencies. For example, I mentioned a radio tuning circuit. So it picks out the carrier frequency for radio 2, for example. We can change this frequency. The traditional way of doing it was we'd use a variable capacitor. If you look at the photograph of the capacitor, the metal plates, when you turn the knob, you're changing the overlapping area. So you're changing the capacitance. Yes, and that changes the natural frequency. Look at the diagram. This is the voltage out against frequency, and you'll notice that it's a peak. Remember resonance. We talked about resonance in the core, and it's a very, very similar graph. In fact, it's an identical graph, only instead of amplitude against frequency, we've got V out over V in is the gain. So it's gain against frequency. Now, talking about band pass filters, there is a quantity which we need to know, which is called the Q factor or the quality factor. Now, the Q factor, it's how sharp my resonance curve is. Okay, if you look at my resonance curve here, that's pretty sharp. If my curve was like that, then the Q factor would be a lot smaller. So the Q factor is a measure of how sharp or how narrow my resonance curve is. How do we work out the Q factor? Well, it's F0 divided by FB. And again, this word bandwidth is coming up again. F0 is the resonance frequency, and I've given you an equation to work that out, and it's on the formula sheet. Yes. FB is the difference in frequencies when the power is 50% of the maximum. Yeah, FB is the difference in frequencies when the power output, the power transferred, is 50% of the maximum. Now, why is it 0.71 there? Because on this scale, I haven't got power, I've got voltage. And you will remember that power is V squared over R. So if the power is 50%, then the voltage is 0.71. Yeah, 71% of the maximum. So remember this, I've seen this come up on a couple of questions. Yes, it's when the voltage output or the gain of the circuit is 0.71 of the maximum. Yeah, 71% of the maximum, because that's when the power is 50% of the maximum. And this is how we work out the Q factor. So this was another video where I've covered an awful lot of stuff, and a lot of it maybe you've never seen before. Here are the key facts. Key facts: capacitors and inductors behave like resistors in AC circuits. Okay, an inductor is just a coil of wire, is an inductor. Their resistance, in inverted commas, depends on the frequency of the signal. A circuit with a capacitor and an inductor in parallel, we only look at the parallel, we don't look at them in series, has a resonant frequency. And at the resonant frequency, the resistance is a minimum. These circuits are analogous to the energy changes for a mass on a spring. To work out the resonance frequency, it's 1 over 2 pi root LC, where L is the inductance, which is measured in Henrys, capital H, and C is the capacitance. The quality factor Q is a measure of how narrow the resonance curve is, and Q is F0 over FB, where F0 is the resonant frequency, FB is the bandwidth, which is the difference in frequencies when the power is 50% of the maximum, and so that's when the voltage output is 0.71 times the maximum. Hope you enjoyed the video. Let me know if you did, and bye for now.